Hi everybody. Sorry for the delay. I had some issues with announcements that didn't go through. And oops, hold on, let me hit this button. There we go. And that sort of gummed up the works when I was working on the, what am I forgetting to do? Oh, I never pushed this button. Okay, so let's see, what are we talking about today for things coming up? So we have a quiz due, or not quiz due. We have lab number 4, that's due tonight. So that's a soft deadline. Try and get that in when you can. We have Maya, who I can already hear because I started talking. There she is. Quiz number 5 is due later in the week. That's the carbohydrates quiz. And then you're going to have a lipids quiz coming up soon, too, once we finish this chapter. Because these biochem chapters aren't that long. This one's only 40 slides. We'll finish it on Wednesday. We'll get pretty close to finishing it today. But yeah, so we're going to talk about lipids today. What is a lipid? Lipids are also known as fat. Oh, I don't know why that did that. I used to have my slides animated. Hold on. And I got rid of all of those, but I must have missed one. So let's do that real quick. And, oh, I didn't get this one either. Okay. There we go. Now it shouldn't, be moving. Okay, cool. Okay. So there's only 2 sections of the lipids chapter. One's going to be just identifying the basic stuff, and then the next chapter, biologically important lipids, is just going to talk about... We are going to talk about some specific lipids that will come up in biochem. And when I say biochem, what I actually mean is like cell bio and anatomy and stuff like that. Maybe not anatomy, because that's more macro scale. But like, how does the brain work, or how do nerves work, or things like that. So we're going to talk about lipids that help in those specific circumstances. And this first part's going to be talking about mostly the energy containing lipids, because we store lipids for long-term energy. And then when we need to digest them, we can break specific bonds so that we can get the fatty acids back. So that's going to be our discussion for this section. So we're going to define a lipid as any biological compound that doesn't dissolve in water. And you might think, oh, that's a lot of things, but it turns out that there's a specific category of compounds that are extremely relevant to biology. Mostly because while we want things to dissolve in water, we don't want everything to dissolve in water. For instance, the contents of cells need to be sort of cordoned off into specific spots. So, like, your mitochondria needs to be separate from your lysosomes, which needs to be separate from the nucleus, which needs to be separate from the endoplasmic reticulum. Like, all of those different areas and regions of the cell have different purposes. But water is pretty insidious. Yeah, insidious. Water will get wherever it wants to because it's tiny and can fit between molecules very easily, unless you have something that absolutely doesn't like water, in which case water gets repelled by it. And that something is, generally speaking in biology, a lipid. So lipids are going to be super important to us because they're going to make up things like cell membranes and here comes Maya. Got it. I don't have my squirt bottle. Maya, stop. You can't hear her, but she's just sitting there going meow over and over and over. Stop. I shooed at her, trying to reach the squirt bottle without taking my headset off. There we go. She just wants to talk to you guys. Alright, so let's look at what lipids are in more detail. We're going to split lipids into 2 categories. Now, we already know what saponification is. Saponification was when we had something like this. So, I don't know, we'll just put some R's here. So I have some ester. And then I react hydroxide with it. And if you remember how this works, what we ended up doing was we put this right here, more or less. I'm trying to get the eraser out there. There we go. Let me write it like this. So O minus H. And then we did this sort of thing. Hopefully you remember that, because that was only 2 chapters ago. And the result that we got was this and some alcohol. So that reaction that we're showing there is saponification. And I'm sort of shorthanding the mechanism so that you can just have something you can remember. Excuse me, my seltzer was a little bit loud there. All right. So some lipids, you're going to be able to do this too, which means that some lipids must be esters. In fact, most of the ones we're going to study are esters. And then there's going to be lipids that specifically you cannot saponify because there are no ester linkages in them. And those are specifically going to be steroids, which we'll talk about later. Now, we're going to see all sorts of different things that lipids can be used for. And the biology of what those do in the body is going to be something you'll study in a different course. I'm sort of just going to lay out the brick foundation for you, and then when you get to biology, you'll be able to walk on those because you'll know those terms. So that's the purpose of this class. All right. So the first type of lipid that we're going to look at is called the fatty acid. So a fatty acid is saponifiable, so that's important to note. And it is basically a carboxylic acid with a long hydrocarbon chain. I don't know why I'm putting R all the way at the end there. Like the whole thing is just R, but something like this. Now, the number of carbons can be anywhere from like 6 to 18 or 20 or even more. And depending on how many carbons you have, how many double bonds that you have, and their positions, you get a different fatty acid structure. And all of these have names. Now, you're not going to be tested on the names like palmitic acid or decanoic acid or things like that. Like, we're not going to talk about specific fatty acids. We're just going to know what the general structure is. And then we're not even going to draw organic structures anymore. We're just going to use a block diagram. And you'll see that in a little bit. So again, it's going to have a lot of carbons on there, and some of them will be single bonded or double bonded. So on the top, I have a generic fatty acid right here. And then down here, I've changed that into this little squiggly line because I didn't really have any other shape to use for hydrocarbon chain. And then I have a circle. And the circle is the polar end. Because this group right here, that's not a great color to use for that, Wes. This group right here is very, very polar, right? The oxygen is much more electronegative than the carbon, so this end is going to have a very strong delta minus, delta plus orientation to it. Whereas the rest of this is all just nonpolar. Now, if I deprotonate this OH over here and make it O minus, so I gotta get rid of this circle here. So if I get rid of this H and I make it just O-, now it's very soluble in water, at least that end. But the rest of the chain is still nonpolar. So this little diagram right here, what I've got, I have two sides. One side likes water. It will dissolve in it because it's charged. But the other side strongly dislikes water because it's all hydrocarbons. And so what we can see is that if I take a bunch of these and I arrange them in a specific way, I can get really interesting patterns. So the first one that we're going to look at is called a micelle. And that kind of looks like this, where if I take a bunch of these and I orient them such that the nonpolar parts all point inward, and then all along the outside I have the polar parts, because these are charged, I get something that's actually soluble in water. Now, this is a useful idea that we can put into practice in ways that you use every day. For example, this is how laundry is cleaned. When you get something on your clothes, like greasy from cooking, or maybe your kids get grass stains because they're playing around in the lawn, or maybe you spill, I don't know, hexane. Hexane would just evaporate, I guess. I don't know. You get stuff on your clothes, but you try and throw it in the washing machine without any soap or anything like that, and it doesn't do anything. And it's because those stains are insoluble in water, because they tend to be nonpolar also. What these micelles do... Is it micelle or micelle? I'm going to say micelle because that's just how I remember saying it. So what these micelles do are, if I take these molecules and arrange them in this fashion, then what ends up happening is the outside part, which is polar, allows the little cluster to be soluble in water. But the inside part is nonpolar. And so what that means is that when I wash clothing that is contaminated with grease and oil, that grease and oil is soluble in the nonpolar part. And so it ends up in here, dissolved into the nonpolar part of the micelle. Then the micelles can be washed away because they're soluble in water, and you can rinse them down the drain. And so you can get rid of the grease from stuff that could be in your clothing. So this is why we use laundry detergent. In fact, detergents are just long-chain fatty acids that have been deprotonated, which is cool. That means that this can be useful for us immediately. So yes, you are cleaning your clothes with fat, technically. In fact, you clean yourself with fat. Soap is a fat. So, no surprise that detergent is too. Now, we can also arrange the lipids in this sort of pattern, where I line up all of the polar parts, and then the nonpolar tails go like this. And so what I make is sort of a membrane. On the outside of this membrane, we have the polar part. And on the inside, we have the nonpolar part. And so this allows us to make a region where water has difficulty passing through it, except in very controlled circumstances. So For instance, the transport protein. We could move water and other things like ions, sodium, potassium, etc. through those channels. But if they tried to move through the membrane itself, well, the water can't move through the membrane because the middle of the membrane is nonpolar and it's not soluble, so water won't dissolve into it. So this is what a cell membrane looks like. You may hear the term lipid bilayer when talking about cell membranes, and that's what this is. You have a layer on the top, and then you have a layer on the bottom. And the two layers have the polar parts pointed outward, so that the parts that are on both sides can allow water to exist on them and mingle where it needs to go. But no water can go in between the lipid bilayer because all of that is nonpolar and it repels water. Which is good because that means that the lipid bilayer would then be held together. Water would probably destroy it because it would try and dissolve it. Now, let's talk more about the shape of the lipid in general. So, we were drawing shapes like this with lines that are kind of squiggly or, I don't know, something like that. In general, the hydrocarbon chain that we describe is linear. And I'm going to put linear in quotes because it is tetrahedral, so it's going to look like this, but it's going to go all relatively in the same direction. And the reason for that, I don't know why I didn't just hit this. The reason for this is because of the physical properties of lipids. So if I have several of these packed together, and their shapes end up like this, maybe because they're not linear, for example, then what ends up happening is that if the surface area that they contact each other with is reduced because the shapes are all over the place, I don't know what a melting point is. Let me try that again. The melting point goes down. And this is a feature that we've talked about when we discussed dispersion forces in Chem 121. So if you have things that exhibit only dispersion forces, which these chains do because they're all nonpolar, dispersion forces require you to have large areas that contact each other for the molecules to stick. We would say that like two molecules that had very long surface areas like this would stick together better than two spherical ones would, because the area that they can form those dispersion interactions is reduced if the shape is spherical and round, as opposed to if it's cylindrical and oblong, then it's increased. So dispersion forces are what dominate how well our lipids can stick together. So if we have shapes that don't line up, then they're not going to be able to stick to each other very effectively, because we want our nonpolar stuff to stick together in order to maintain the shapes that we see, so either the micelles or the lipid bilayers. So what that means is that with our fatty acids that we're going to be looking at, there must be various orientations, and some of those must be really, really, really linear. So that's what we're going to be discussing today. Is we're going to be talking about which orientations will give us a straight line and which ones won't. In order to do that, we're going to classify our lipids into two categories. The first one is called an unsaturated fatty acid. Unsaturated fatty acids do not have any double bonds. Oh my goodness, I'm so sorry. That's wrong. Fatty acids contain double bonds. Those are unsaturated. What am I saying? Saturated fatty acids do not have double bonds. Just like we were talking about hydrocarbons. We were talking about double bonds before in the alkenes chapter. Something is saturated if it has the maximum number of hydrogens possible. Man, I'm on autopilot today. I'm just tired. So, no double bonds is a saturated fatty acid. I apologize for misspeaking there. Now, why do we care about double bonds specifically? And that is because when I have a double bond, remember that double bonds can make a cis or trans orientation, right? And if I have a cis orientation, I'm going to cause my molecule to kind of bend. We're going to see that in just a second here. Whereas if I have a trans orientation, then it looks relatively linear. And if I have no double bonds at all, so just a saturated fatty acid, then it still looks relatively linear to begin with. All right, so here are some examples of fatty acids. These are all saturated. None of these have double bonds in them. And you can see that the names aren't even close to systematic. Like, these are just names that were assigned to these. So you might remember palmitic acid that I said before, because that was the only one I could think of. And they're just all, oh, okay, these have longer and longer and longer chains. Nothing super exciting there. Now, if they're in this orientation, where they're linear, and they just go straight out like this, if I were to cluster these all together, then that would be effective at having my dispersion forces line up so that they could interact with each other. So this contact area between these molecules is high because these are linear. But let's talk about when we have unsaturated fatty acids. And so you could see that all of these that are in the cis orientation, remember that cis means that, oh, the important stuff is on the same side of our double bond here. So every time I have a cis double bond, it causes the fatty acid to kink in some direction. And you can see that these bends that we have here change the direction that the fatty acid is, and it makes them a lot harder to line up with each other so that you can get the dispersion forces to interact with fatty acids stacked adjacent to each other. So we can define unsaturated fats a little bit further. So a monounsaturated fat has one double bond. Something that's polyunsaturated has more than one double bond. And again, the geometry that we care about here is the cis geometry because that's what causes it to bend. If we had the trans geometry, then the molecule would actually look remarkably linear. And that can have issues when we are examining the geometry of the fatty acid and also its reactivity, because single bonds don't react, but double bonds do. And so you can do interesting chemistry with double bonds, but maybe you don't want to do that. For example, if you are just using something as a lipid bilayer, it probably shouldn't be reactive, right? Because if something passes through your lipid bilayer and then ends up reacting with said bilayer, it's no longer a lipid bilayer. And that could cause issues. So, you may have heard about how trans fatty acids are not great for health, and that's one of the reasons why, is because the body would end up sticking them where they would put saturated fatty acids, and then stuff would react with it, and that's not something that you want. Or at least your cells don't want that. Whereas cis fatty acids, because their shape is different, you can't put them in the body in the same place as you'd put not trans fatty acids, but saturated fatty acids. Excuse me. All right. And so there's some examples of that here. This is oleic acid. Oleic acid has a double bond in the middle of it. And if I have the cis orientation here, you can clearly see that the shape is going to be different. So that if I was trying to put these into a lipid bilayer, I would get something like this. Can you tell which one is the cis oleic acid? Probably, right? And so this would not pack in as effectively because it's bent. Now, this is an interesting point to bring up, even though we've discussed it already. If I have a sample that is just unsaturated fats, or fatty acids, I should say, they will not pack as tightly and the boiling point will go down, and I will end up with something that is a liquid. But if I have something that becomes more saturated, it tends to be more towards the solid phase. And so this is going to lead us into things like butter, where butter is sort of a semi-solid, and you can control how solid the butter is. And a lot of that is going to be, well, okay, can I turn this into a saturated fatty acid? And the answer is yeah. We talked about how to do that in the hydrogenation reaction in the alkenes chapter. Remember how if I have a double bond and I add hydrogen over some sort of catalyst? I hope you remember, because you still got to know it. You could then break the double bond, and this would work for either of these, because all we care about is the double bond there. So we could turn unsaturated fatty acids into saturated fatty acids. But what we're going to do specifically is we want that to go slowly, because the more fatty acids I convert from unsaturated to saturated, the higher the melting point will go, because as things get saturated, they become linear and they would all pack together effectively. So if I bubble hydrogen through unsaturated fatty acids in the presence of some sort of catalyst like nickel that's slow and controlled, I can observe what it is that I am making and then stop the reaction by stopping the addition of hydrogen when I get to the melting point or the thickness that I want. And this is how we get partially hydrogenated saturated fat, or partially hydrogenated oil, or things like that. You've probably heard some of these terms before just by looking at stuff like on the side of the margarine or butter or cooking oil packages. You've probably heard of these terms. All right. That's literally the same slide as before. I don't know why I have that slide in there. Now, getting to the more overall view of the molecules that we're going to look at, we're going to use the terms fats and oils when we're talking about things that we use every day. The only difference between fats and oils, and I think I have it on the next statement right here. So a fat is a solid at room temperature, and an oil is a liquid at room temperature. So fats and... Wow, I lost my cursor there. There we go. Oh, come on. I'm trying to change color, and it's not helping me. There we go. An oil is liquid at room temperature. There we go. So to be correct in our terminology here, if I were to ask you, like, which of these correctly describes butter or margarine, you would say fat. But which of these would describe... I'm trying to think of what cooking oil would be called without using the word oil. But I really can't come up with it, and it's just an oil. So, oils are liquids. We use them for different applications in specifically cooking, because I promised I was going to talk about cooking. For example, you would not want to cook grilled cheese by putting your bread in oil. Like, that, it would get soggy unless you had the oil really, really, really hot, right? Oil is good for certain things, but bread, probably not the best choice for it. And somebody out there might just beg to differ, like, well, I make grilled cheese with oil, and it's just fine. It's a little bit greasy, but I like it that way because I was raised that way. Like, and that's great, but in this household, we use butter on our grilled cheese. I don't know. So there are specific applications where you'd want to use butter versus oil. Now, the materials that are used to those, the fatty acids, are pretty similar. It's just that in fats, since they are more solid, we're going to have more saturated fat in butter than we would in, say, olive oil or canola oil or whatever oil it is that you use for cooking. I use all sorts of different oils because they all have different flavors. Olive oil is probably my go-to. My second favorite was probably chili oil because you get spicy oil. So that's great for making fried rice. All right. Let's talk about how we take fatty acids and actually make what we would call a fat or an oil. So the first step is we need to get 3 fatty acids. And they don't have to all be the same type. So these can all be unique if they whatever application you were looking at does that. And then what you're going to do is you're going to get this molecule here. This is glycerol. You might remember from a long time ago where I said, remember this molecule, 1,2,3-propane triol? It's going to become important later, and this is that part. If I have glycerol and I use one of the hydroxide groups to form an ester linkage, then I will make water. There's my water right here, those two. And I will turn the fatty acid into an ester. Now, if I do this 3 times with all of the alcohol groups, I get a triglyceride. The tri part means that there are 3 fatty acids on there. Now, which triglyceride you get depends on which fatty acids you use. Obviously, there are all sorts of different combinations of fatty acids that you could put in there. So you could put in just saturated fatty acids and get a specific triglyceride. You could have any different combinations. So if I had like some that were 10 carbon and then the last one was 12 or whatever, you get a different fatty acid. And then you can start substituting unsaturated fatty acids in there. And you get all sorts of different combinations. Now, because drawing that picture becomes very, very, very cumbersome, we're going to reduce the picture down to this block diagram over here. So this is my block diagram. Now, just because it's written as a block diagram does not mean that you don't need to know what goes in the blocks. So writing the word fatty acid is in the block is important, but knowing what a fatty acid is also important. So I am using the block diagrams because, one, I'm lazy, and I already know the chemistry, so that's another reason too. But two, because it takes a lot less time and space for me to communicate the same idea once we understand what these are. So we're going to be working with block diagrams quite a bit in this chapter and the next few chapters as we go through our discussion of lipids. All right. Now, for the most part, when we make triglycerides, the fatty acids are not often identical. Most of the time, they're unique. I don't really have a good explanation for that. My best guess would be abundance. So if I have several different fatty acids that are abundant, odds are I'm going to get just a random assortment of molecules that are attached to my glycerol. It'd be kind of like if I had a bag full of red, green, and blue marbles, and I said, reach in and pull out 3. The odds of you getting all blue, not very high. You're probably going to get some sort of mixture. Now, what do triglycerides do? Well, your body turns fatty acids into triglycerides, and then you get to keep them as fat for energy storage. And then when you need the energy later, you take your fatty acids and you hydrolyze them back into fatty acids, which you can then use for energy. Now, as far as the chemistry that we're going to be looking at is concerned, we've already looked at the reactions. So we've already looked at saponification. And we've already looked at hydrogenation. So I need a better color than that. So we've already looked at saponification. We've already looked at hydrogenation. So you should be familiar with these reactions, but we're going to look at them anyway. I was just reading the slide and I'm like, wait a second, this isn't either of those reactions. This is just what your body is doing to turn triglycerides back into fatty acids. So remember how we said we can hydrolyze the ester linkages right here. So those break. Now, in our reactions, we discussed that in order to hydrolyze something, you need to have a source of acid available. Now, if this happens in your stomach, to turn stuff into fatty acids to make it easier for transport, then yeah, you have abundant H+. But in your cells, not necessarily abundant H+. So we have something else, and that's called lipase. Lipase is what's known as an enzyme. We're going to talk about enzymes in the next chapter. And using either of those is going to allow us to split the ester linkages. Again, remember, these are all ester linkages right here. So this and this and this. Now, the next thing that we can do is what's called saponification. You might think, well, that sounds kind of like soap, except somebody misspelled it, right? And yeah, saponification is actually how we make soap. What we do is we take a strong base. Sodium hydroxide is very cheap and available, so we use that most of the time. When you mix sodium hydroxide with the fatty acid, you break the ester linkages. But because you're doing it under basic conditions, you can't have a carboxylic acid. So this, which is something that you would normally make when you hydrolyze a bond, under basic conditions, that H is gone. And you have this. And then you have glycerol, which just hangs out, because that's what's left over. So saponification will do the same thing as hydrolysis, but we don't need any specific enzyme because hydroxide is very reactive. And we get a different result at the end. We get the carboxylate salt. And this material right here, this is one of the ingredients used in soap. So we'll even call it the main ingredient. Because without this, you don't have soap. And this slide is just telling us everything that we talked about before we were showing the micelles. So, and I think I have pictures. Yeah, here's our micelle. And so if I have something that's grease, grease would be nonpolar or otherwise insoluble in water. So when I have my micelles from my soap fatty acids, dissolve my grease in there, it gets stuck in here, just like we said before. And then the stuff on the outside is water soluble. But it's only water soluble because all of these have negative charges, so that helps it solubilize a lot more. Can I explain how glycerol in the body becomes the triglycerides that we don't want? Not very effectively. So glycerol. So let me draw a generic glycerol molecule here. Glycerol is sort of our template. So glycerol is just everywhere because it is the backbone of triglycerides. So you have it in your body because you have fat in your body, because fat is a necessary component for health. And other animals or plants that you consume also have it in them because they have triglycerides too. And so whatever you attach to these, so if I get rid of these H's here, I'm just going to go like this, 1, 2, 3. Whatever 1, 2, and 3 end up being depends on really your diet. So as you consume fatty acids, available glycerol will then form fatty acids to them. And if you consume fatty acids that are not necessarily healthy, for example, maybe you eat like all the red meat ever. Inside red meat could be, and I'm speaking of this because I'm not a dietitian or a nutrition expert. Inside red meat could be a higher percentage of fatty acids that you don't want. And then if you consume them, you would digest them, you would hydrolyze them into fatty acids on their own in your stomach, and then your body would see them and say, oh, you're a fatty acid. Let's stick you on a glycerol. And then you would get that in your body. So that's like the general process, but like specifically, like how do we synthesize these triglycerides? Well, we don't make the fatty acids ourselves. We consume them in our diet from other sources. That's about as much detail as I can go into because that's about as much as I know. Past that, we get into biology, and I'm not a bio background person. I'm an inorganic chemist, so like I find so I say inorganic, but I'm also an organic chemist. I did both. Um, because I found both interesting, and there is actually a field of chemistry where you can do both. But as far as like cell biology is concerned, like I studied that very, very briefly, and I only have a general understanding of what's going on. And that's my understanding, is that one, we can make it if we have the pieces. Two, we get the pieces from our diet. That's basically it. I hope that answered your question. I feel like it did, but probably not to the level of detail that I wish I could provide there. I need to check something really quickly. Where we are in we're almost done with the lipids chapter. Okay, so we are due for a break shortly. So I want to ask the class here, before we take the break. So I obviously don't have the lipids quiz written yet. I have to write that either Thursday or Friday or something like that. Yeah, so before we take our break, I could see this going kind of two ways. So I was only planning on doing lipids this week. I didn't realize that we could do this in 2 hours instead of 4. Do we want to finish the chapter today and then have no class tomorrow, or do we want to stop now and do the second hour tomorrow? Like, whatever people want to do, like, type something in the chat and let me know. I'm happy to keep going today. I'm not going to have enough material to go over for 2 days worth. So we can either stop early and then do another hour tomorrow, or we could do both hours today and then just not show up tomorrow. And then I'll use that time to just write the quiz. And I'll probably finish it on Thursday or Friday or something like that. So I'm going to let you decide what you would like to do during the break. I suspect people are going to want to keep going, and then we'll just take our day off tomorrow. But if anybody has any opinions on what to do with the class time, let me know. See, yeah, I'm already getting feedback like, yeah, let's finish it today, and then we don't have to come to class tomorrow. That's totally valid, and that's what I sort of expect people to want to do, because we can totally finish the rest of the chapter from here. Because after this, we're going to talk about how to hydrogenate, which we've already done. I'm going to talk about waxes. Waxes are basically fatty acids, except instead of glycerol, you have another hydrocarbon. And then it's just like, what are the specific biological lipids, which is just, here, memorize these block diagrams and know what these linkages are. Like, one is, instead of a ester, it's an amide. And then you connect phosphoric acid to a choline or something like that. And like, it's really just going to be like, remember these structures when they come up in cell bio, when you're talking about sphingosine and stuff like that. So I'm going to start the timer. Let me know what your opinion is on this while we take the break. And I will see you in 10 minutes, and we'll do whatever it is you decide to do. Okay? See you shortly. Oh, but this is one of my favorite songs in this track. That's too bad. Alright, we'll wind this down here. We'll have to start with that one whenever. Alright, so it looks like everybody wants to finish this today, so we'll probably be able to finish it. Actually, we'll definitely be able to finish it. Excuse me. Alright, so let's go to hydrogenation. Let's talk about hydrogenation real quick. So, sorry, I said something and then I immediately heard meow behind me, and now she's running away because I'm talking again. I was petting Maya during the break, and now she must leave. She must go. Alright, so remember that if you take a fatty acid, I have no idea if this is going to appear when I hit the spacebar. Yeah, there it is right there. Okay, so I won't draw the reaction. If you take a fatty acid that contains double bonds, so any unsaturated fatty acid, and you add hydrogen to it, you will then make it a single bond. And so the overall thing that we care about here is that if I reduce the number of double bonds, the melting point will go up. And the reason for that is the more linear my molecule is, the more dispersion forces can be formed because they would all the parts of the molecule would all align with themselves. Now, the effect is that if I do this enough, I will make a semi-solid, or I will make a liquid into a semi-solid. And I could even make it more and more and more solid. Now, this actually came up in Canadian news recently. I read an article about how people said, man, what has happened to Canadian butter? It's not as spreadable as it used to be. It feels like it's more solid. And that's actually a thing that can happen. And so what they deduced was that the feed that was going into the feedstock for the cattle that they were gathering milk from, I think they were adding more like palm oil or stuff like that. And that turned out to be something with maybe fewer double bonds in it. So when that was hydrogenated, the resulting product of the butter that they got was firmer than the original product because the food that they were giving the cattle had changed. So it's very possible to make minor changes and then to get a totally different result at the end. So all of this is kind of connected. Which goes back to the question that we had earlier about, like, how do you get these fatty acids in you? And it's all food, right? All right, so here's our picture of it. Let me get rid of the cursor here. Oops, hit the wrong button. So if I take my double bond and I add, oops, sorry, hit the wrong button. I add hydrogen in the presence of a nickel catalyst, that segment would then become linear. Now, the reason that nickel is used is because nickel is much, 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 much more slow than platinum is. Platinum is very rapid at dehydrogenation. This is very good. But nickel is not as effective. It's much more slow. Now, the result of this is that when using nickel, you have a lot more control over when the process is done. So you get partially dehydrogenated fatty acids. So this is how partially dehydrogenated oil is turned into things like margarine or butter. And we've already talked about all this. So, depending on what application you want to do, you might prefer a solid or a liquid. So, like, frying your chicken, using either butter or oil is fine. I think I would prefer oil for that because it would be easier to get, like, to make sure I have a high contact with my fried chicken when I put it on the skillet or whatever. But for things like bread has too high of a surface area. It'll just soak up all the oil, and that's not what I want. I just want the butter to get just the surface of it. All right, so let's summarize our triglyceride chemistry here. Triglycerides form from glycerol and 3 fatty acids put together. We make ester linkages out of them. That's probably the most important part of that process. Is that's the bond that we make, and that's how we can undo that bond using the chemistry that we've talked about. So that would be hydrolysis. We could also saponify, and then we can hydrogenate double bonds. All right, what is a wax? So waxes are another family of lipids. You can saponify waxes, but it's kind of not really much of a reason to do that. The only difference between a fatty acid and a wax is that instead of connecting this part right here being the glycerol in a fatty acid, in a wax, it's just a long chain alcohol. So the highlighted part that I have green there, that would be my glycerol connection. But in a wax, instead, you just have a long carbon chain. So you have something that is very, very, very nonpolar on both sides here. Now, where do waxes occur? Waxes typically occur on the surfaces of substances that need to be protected from water. So leaves, fruit, leather, these are all things that have waxy surfaces. Because waxes are so insoluble in water, they're essentially just used to waterproof surfaces of things. So, like when you buy an apple, if you look at an apple, it's very shiny on the top. That sheen that you see on an apple is the waxy surface of it. So if you like wash an apple, your water won't soak into the apple effectively. It'll instead bead up on the surface so that the apple won't rot while it's hanging on the tree if the tree is growing in, say, rainy Washington, right? Like, we don't want our fruit to immediately rot. Because fruit specifically has a purpose. It is to provide an energy source for the seeds and transport for the seeds that are in there, right? We just happen to eat it because fruit is delicious. Fun note, Crisco stands for crystallized cottonseed oil. I don't think I knew that. That makes sense, though. Now that I'm looking at the name. That was a fun note. Most fun notes or fun facts aren't that fun. That one, though, I think was fun. All right, let's talk about specific lipids that you're going to encounter in biochem. Now, for these, I'm going to almost exclusively use block diagrams. I'm going to show you the initial structures at the start. But then afterward, we're just going to substitute out parts of the block diagram. And you'll need to know what those block diagram pieces are and what connects to what. So, like, for example, what is sphingosine and why is it different from glycerol? Like, that's an important thing to know. But in our diagram, we're literally just going to write the word sphingosine or glycerol. All right, so the first complex lipid that we're going to talk about is the phosphoglyceride. The only difference between a phosphoglyceride and a regular triglyceride is that one of the 3 triglyceride groups is going to instead be a phosphoric acid, which then attaches to what's called an amino alcohol. An amino alcohol is just an alcohol that also has an amine at the end of it. And so that looks kind of like this. So here, sorry, the cursor's right in a bad spot. Now, it doesn't have to be this bottom one. It could be any of these 3, but one of these is going to be phosphoric acid and an amino alcohol. I don't actually need it. I was going to start drawing these. I have the structures in here already, so we know what phosphoric acid is. It's this. But specifically, it's the PO4 part that we care about. So let's identify the bonds here, because that's what I care about, right? So this right here is a phosphate ester linkage. And now on this part, I have labeled the amino alcohol as this part, but technically this is also part of the amino alcohol too, really. Because what an amino alcohol would look like would be HO, CH2, CH2, that. And so when you do that, you aren't really making an ester linkage. Well, I guess you are, technically. So this would also be a phosphate ester linkage. Because the phosphate is the part providing the double bond, or the simulated carbonyl. Now, the phosphoric acid is going to be really soluble in water because it has this right here, and the amino alcohol also has a charge here. So you might think, oh, okay, this increases solubility. But what we're going to talk about later, we're going to talk about something called a Zwitter ion, which actually has a very interesting property. We're going to talk about that in the protein section and also in the lab for next week. So are these as soluble in water as you'd think? Not as soluble as you'd think. They're a little more soluble because they're charged, but there is an interesting thing that goes on when you have the same, or I'm sorry, not the same. You have opposite charges separated on a molecule like this. So it does increase a little bit, but not as much as you'd think. We'll talk about why that is in the next chapter. All right. This on the screen is what's called sphingosine. This right here is a really, really long chain hydrocarbon. And then we connect that to what looks kind of like glycerol on the very top or on the bottom. But in the middle, we have an amine instead. So what ends up happening in sphingosine is that we make connections from here and here. We only use 2 positions on sphingosine. Now, in theory, you could attach a third group. I actually don't know why the third group doesn't attach there. But the examples that we're going to be looking at only contain attachments to both the amine and the alcohol on the molecule. So when you have a sphingosine, you're only going to have 2 connections to it. When you have a glycerol, you're going to have 3. And so that's going to look, I'm just going to skip ahead to the diagram here. That's going to look like this. So we're only ever going to attach the bottom 2 for this. Now, there's 2 types of molecules that we're going to talk about here. So the first one is sphingomyelin. And so a sphingomyelin occurs if you attach the hydroxy group to a choline. And we'll show what choline is in a second. And then secondly, if you attach the hydroxy group to a carbohydrate, you get what's called a glycolipid. So here's what choline looks like. Choline looks like the amino alcohol that we were talking before, but specifically this amino alcohol is choline. What the heck was that sound? My cats are knocking things over, probably. That's okay. Now, the linkages in a sphingomyelin, same as before, because we're connecting the phosphoric acid, and this was an OH. This would be an O connected to my phosphoric acid. So this will be a phosphoric acid, or not phosphoric acid. What am I saying? Phosphate ester. I'm thinking of the molecule, not the bond. So phosphate ester. And this one will be 2. Now, where do you find sphingomyelins? Most of the time, they would be in brain and nerve tissue. Unfortunately, as far as like the biological use of these is concerned, I only know how to make them. I don't know much beyond this, unfortunately. I know that glycolipids are also in brain tissue. And then the difference here is that instead of having a phosphoric acid, I just have a carbohydrate. And so this right here I form a glycosidic linkage to the sphingosine. And here's my anomeric carbon. And so that connection is my sphingosine right there. And again, also in brain tissue. So these fatty acids will come up, I assume, in biology because the textbook makes specific mention of them. So they must be important enough. And there's our summary. So phosphoglycerides are like triglycerides, except I have a phosphoric acid and an amino alcohol in one of the fatty acids. It says specifically here the bottom fatty acid. I don't know if it is specifically the bottom fatty acid. Off the top of my memory. I thought it could be any one that you want because it's you just flip the molecule around, right? I have to think about that, but anyway. So we have that category of complex lipids, and then we have sphingolipids, which are sphingomyelins, which is fatty acid, phosphoric acid, choline. And then glycolipids are sphingosine, fatty acid, carbohydrate. All right, last category we're going to talk about are steroids. You've probably heard of the term steroid before. Probably in reference to sports, because steroid use in professional sports is definitely a problem that occurs, but it's kind of the main thing that I can think of that as a scientist, I hear these sciencey words all over the place, but this is the context that I know it mostly from. And in fact, steroids are a lot more common than you'd think. A steroid is specifically a fatty acid that is not saponifiable. Now, I don't actually like the word fatty acid here because there aren't really fatty acids in here, so I'm going to change this to lipid. There is a very specific structure for a steroid, and it looks like this caterpillar, which is why I put it in here. If you've played Super Mario World, you know what Wiggler is. And I'm showing my age here because this is a video game from like 1991. But the structure of a steroid looks like a caterpillar, and it goes like this. So 6, 6, 6, 5, where the 5 is his nose. Now, it's a caterpillar because it has this up in it. Otherwise, I would have just made a line or something, or a worm or whatever. So this is the basic structure of a steroid. And these rings all connect in this specific pattern for all steroids. It's very, very common. In fact, one of the most common steroids is something that you probably eat too much of every day. It's called cholesterol. So speaking of cholesterol, here it is. This is what cholesterol looks like. Cholesterol is kind of a template. We use cholesterol as the starting point to make various hormones and bile salts. Now, most of the cholesterol molecule is insoluble. In fact, if I circle all of this part right here, this is why eating too much cholesterol can be an issue. Since we need to transport cholesterol through the bloodstream, if you have too much of it, I mean, it could cake onto walls and things like that of your arteries, and that would be no good. Now, another thing that I have read and or heard is that in the event that you have an issue with your heart, cholesterol tries to fill in the gap so that like blood doesn't so if you had an artery that like hardened or cracked or something like that, and then there was a rupture or something like that, cholesterol is the first on the scene to like stop that and fill it in, which is good because it's completely insoluble. So things like water would not pass through it. And I'm getting squeamish just talking about that because I don't like talking about blood. so let's not talk about that. Anyway, there are only two functional groups on cholesterol. Here's one and here's the other. But you can do quite a bit with those two things. Enzyme activity will take care of the rest of it, so it'll cleave off other parts that we might not want. All right. Now, your gallbladder secretes this steroid that is used to break down fat. Now, bile salts help us digest fatty acids because fats tend to be very nonpolar. So we need something that is both polar and nonpolar. And so this has a lot of polar components to it that help it dissolve effectively. But it also has just as many nonpolar parts to it. So this is sort of like the Goldilocks just right molecule for dealing with fatty acids. This helps us break them down into smaller pieces so that we don't end up with just a bunch of me cells that pass through our body. Now, if you had a bunch of me cells for your fatty acids in your stomach, then what would end up happening is that they would just pass straight through you. The water insoluble parts would all point towards the center of the me cell. The water soluble parts would all point outward, and then no enzyme could really get into that. So what biosalts do is they tend to break up those me cells. Now, biosalts form in the gallbladder, and if your gallbladder gets like diseased or becomes problematic and you have to have it removed, then what ends up happening is that if you consume too many fatty foods, you start to feel ill. And it's for this reason, because that's the purpose of what the gallbladder does, is it makes these bile salts to dissolve down and break down those globules of fat. I have several friends who've actually had their gallbladders removed, so this is pretty common. And when I say common, I mean like of the hundreds of people that I know, 4 have had their gallbladders removed, so it's common. I mean, like the odds are in your favor that you will not have to have your gallbladder removed. But if you do have gallbladder surgery, don't panic. It's going to be okay. My best friend had his gallbladder removed, and he is basically back to normal. All right. What else do bile salts do? Bile salts are used because they have a significant nonpolar part to emulsify cholesterol. So what does that mean? We can collect cholesterol, and then we can use these bile salts to get it to the kidney so that we can force it out of the body. All right. What other steroids are out there? You've probably heard of what are called hormones. So you've probably heard of testosterone or estrogen. These are both steroids. So I don't know if I have pictures of them. There they are. They're right here. And you could see the caterpillar shape in both of these. Now, all of these molecules have tons of functional groups on them that can do various things. Excuse me. I ran out of water, so now I'm really thirsty. So, cortisol, for example, has a carbonyl group. We've got a bunch of hydroxides are all over the place. Here's another carbonyl and a double bond. Estradiol has some alcohols. It also has this benzene functional ring. And testosterone has molecules that are pretty similar to, not molecules, functional groups that are pretty similar to cortisol, but some of them have been, have been removed. Yeah, if you had multiple people in your family have their gallbladder removed, then you definitely know that's like, oh man, that might happen to you, but at the same time, it's a pretty minor surgery. The scary part of gallbladder related stuff is leading up to it. So, like, the pain that you get is borderline ridiculous, and then you have surgery, and then you end up being okay. On the previous slide, I'm going to go back to the previous slide, just because these have descriptions of what these molecules are. So the first one's cortisol. Cortisol is an anti-inflammatory agent. So you might have heard of specific creams called like cortisone 10 or things like that. And those creams are specifically for things like itching or rashes or whatever, because they are anti-inflammatory. Other things that cortisol do is it regulates how much blood sugar, like glucose and glycogens, that are available. And then down here we have sex hormones. So testosterone and estradiol are just the molecules that govern the development of sex characteristics, generally like through puberty, and they do biology stuff. I don't really want to talk about what sex hormones do, because we kind of know, right? It's not a sex ed class, but testosterone and estradiol are the precursors that lead to the biology that we care about for those. And really all I care about is that, hey, these are functional groups, but they are steroids because you can see the caterpillar in here. Here's my caterpillar. All right. The last type of molecule that we have is called the prostaglandin. The prostaglandin is not really a steroid, and it's not really a fatty acid, but it's kind of like a little bit of both. But they're common enough, and they originate from these 20 carbon chains. I cannot click on the highlighter. There we go. So prostaglandin has the cyclic thing right here. So it's cyclic, and it comes from a 20 carbon chain. And what we end up having here is, so the parts of the prostaglandin, you have a carboxylic acid, you have the cyclic part, and then you have other features on here that are going to be useful. So this specific prostaglandin that's shown here, this is called PGE2. And a common use for this is to induce labor. Oops. Now, prostaglandins are useful for various applications, and they're common enough that I just threw in the structure there. Again, I care more about the structure than the uses because, again, that's sort of getting into biology. Like, why do prostaglandins help for blood clotting? Like, what mechanism is that? I don't actually know the answer to that because I haven't studied that. But if I had to guess, like, what are the important parts of the prostaglandin? Like, I would say, like, oh, well, these two things are in close proximity to each other. I bet they're important. So I would guess something like that's probably important, and this one's probably important. So, like, if I were to just look at this molecule and have no idea what else it did, I would say it probably does things here. I think you have a typo in there, and I can't decipher it, unfortunately. Pitocin might be a brand or generic name that I've never heard of before. Let me Google that real quick. Pitocin. Oh, oxytocin. Okay, yeah. So, I believe that that is what this is. Oh, okay. Hold on. Here, you can say hi to everybody, but only because I'm ahead of schedule. Hi. Yeah. Do you have anything else you want to say to them? She wants to make a video, but I don't have a way to record you. I guess I could record you on my phone. Alright, so what specifically do I care about in this chapter? This is the last slide, by the way. I think it's the last slide. Let me check real quick. Yeah, it is. Okay. So we covered all sorts of crazy stuff, so I'm going to just put all this text on the screen here. What specifically do I want you to know? So I want you to know general structures. So for example, if I send you a picture of a lipid with specific linkages, I want you to be able to tell me what lipid I am referring to. So know the general structures of all of these things. So like I might ask you a question. Here is a molecule. Which of these would you categorize this as? Or I might ask you something like, okay, we know about non-steroidal anti-inflammatory inhibitors. So if it says non-steroidal, what does that mean? Well, it's not a steroid. Okay. Which of these would be a non-steroidal anti-inflammatory inhibitor? And if I gave you a picture of cortisol, you'd probably go, oh, that's a steroid. Steroids can't be non-steroidal, so there you go. So that sort of stuff. So make sure that you know the general structures, because I'm going to be providing you the pictures of the molecules, and it'll be your turn, your job to line those up with the definitions and answer the questions I'm asking you. So, other things that I want you to know the different reactions that we've been looking at. So, know how to make ester and amide linkages, what hydrolysis that we perform, and when, etc. And then finally, know the chemistry and the chemical and physical properties of the stuff that we're looking at. So, why does hydrogenation matter for saturated versus unsaturated fatty acids? Like, why do we do that? Why do we care about hydrogenation at all? Things I'm not going to test you on. I'm not going to test you on specific names. So I'm not going to be like, which of these is stearic acid? Don't care. Which of these is testosterone? Don't care. I'm not going to ask you where things appear. So I'm not going to tell you, like, or I'm not going to ask you, in which biological system do sphingomyelins appear? Because I don't really care about that. Like, yeah, it's brain tissue and nerve stuff, but that's not really what interests me. I care more about the chemistry. I want you to tell me what the bonds are, how I can form the molecule, and then once you know that, you can go to Cell Bio, and they'll tell you what the molecule is used for. And then down here are just some example questions that you're going to see on this quiz. Would this molecule be soluble in water or fat? What functional groups are present and what they do? And then if I do this specific reaction, what will happen? All right, that's all I got. That's the lipids chapter. So we can get our celebratory orc here. Here he is. And that's all I got. So if you have any questions about lipids, let me know. I will put a quiz online at some point this week. since I have plenty of time to just go over just some extra details. Can I write on this slide? Oops. Hold on just a second. I'm not sure if I can actually draw on the last slide here. No, it won't let me. Okay. So what I'll do is I'll just go over here. We'll move this out of the way. Now that I'm trying to think about that, I don't even remember what I was going to say here. So, oh, okay. So let's talk about week 10. So week 10. So these are really the only things that we have left to talk about is proteins and nucleic acids. So we're going to do those next week. We're going to spend most of the time on proteins, and then like in the last 10 minutes of the last lecture, I'm going to throw a bunch of nucleic acids on the board and just be like, this is what nucleic acids look like. Any questions? Okay, good. Because we don't really talk much about Unit 19. At that point, we just start to veer hard into biology. And again, I don't care about naming enzymes. I don't care about like memorizing a cycle. I want to know more about the bonds and the molecules and like how you construct the molecules and what the specific molecules do. So that's what we're going to be doing in the proteins and nucleic acid section. Let's talk about the quizzes. So the remaining quizzes. So there's going to be a quiz on chapter 17. And then there's going to be a quiz on proteins and nucleic acids. I misspelled that. Nucleic acids. So there's 2 more quizzes left. And those will be due before the end of the quarter. And then you have exam number 2, which is going to be early finals week. So like it'll be assigned Monday or Sunday or whatever I said on the syllabus. If it's Friday of next week, I'm going to just move it back to Monday. And then you have the final exam after that. So, oh, and then there's lab number 5, but we're going to talk about that next week. Lab number 5 is super easy. I wrote it last night. The lab is different than what is said in the syllabus. So I said there would be a lipids lab, but I could not find any extra information about the lipids lab from the materials I'd been given, and it wasn't very good. So I found a different lab that I thought was a little bit better. And you're going to watch a video of how they isolate a protein from milk. And then answer a bunch of questions about it. So lab number 5 is really, if you do it, you get 20 to 25 points. I give you 5 points for just turning it in. Like, everybody gets 5 points for that lab. So yeah, so that's where we're going. We are almost done with the quarter. Yeah, at the end, all of the work kind of piles up, so I know that people are going to be busy, and I'm going to be busy too, so I totally understand. But hang in there. We are very, very close to being finished with the class, and if you've made it this far, then you can definitely make it to the end. All right, I want to thank everybody for coming out to the lecture. There will be no lecture tomorrow for Chem 131 because we covered everything I thought we needed to. The proteins chapter is a little bit long, but I don't think that it's worth me saying, oh, we have to get together on Wednesday and do half of proteins because, I mean, let's take our day off now and save those problems for future us, I guess, right? All right. So I'll see you next week. Monday will be a lab number 5 and Q&A, and then Tuesday and Wednesday next week will be the last lecture. See you then.